All right, so as we start this 5-7 video out, I just want to give you guys kind of some synonyms, some words that are really similar. So like when I refer to any of these words, what the differences are and really what it means. So for example, and you're not going to have to know how to solve this, I'm just going to give you these answers here. The zeros of this particular function are -3, -2, 1, and 2. So what zeros are when you set the polynomial equal to 0, what the solutions would be. So then you'd say that the roots of p of x equals 0 are the very same numbers. So zeros and roots are very, very similar. You use roots to refer to any function. So you'd have to specifically set p of x equal to 0, but the definition of zeros would be any value that make a polynomial equal to 0. So these are very, very similar. Factors, if you could break this down into factors, they would look like this. X plus 3, x plus 2, x minus 1, x minus 2. And you can see that each of these zeros and roots correlates to one of these factors. If we were to set each of these equal to 0, we would get these four numbers, which means, very similarly, the x-intercepts are those same four numbers. Okay, so really quickly, let me show you what the graph would look like. So we've got an x-intercept here, 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 and here. And your graph looks something like this. All right, so remember in the previous sections we talked about how an x to the fourth would kind of make this W like this, and both ends would go up because this is a positive even degree. All right, so that leads us to something called the fundamental theorem of algebra. It's kind of related to all of these things right here. The fundamental theorem says this: every polynomial with degree greater than 0 with degree greater than 0 has at least one root. Oops. Has at least one root in the set of complex numbers. Okay, so now notice, we don't just say real numbers, we say complex numbers, because you could have those imaginary or complex answers as well. So any function, no matter what it is guaranteed to have at least one root. Meaning, if you set the function equal to 0, you're guaranteed to come up with some answer. Real, imaginary, positive, negative, decimal, fraction, whatever. This theorem guarantees that you'll come up with something. So let's go through and solve these equations. All right, so this one right here, x squared plus 2x minus 48 is pretty run-of-the-mill quadratic. You might want to solve it by factoring first and see if that works. Otherwise, we've got backups. So let's start with x and x. Don't forget your equals 0. So whatever goes in here, we want them to multiply to -48 and add to +2. Okay, so we know it's going to be one negative number, one positive number, because that's the only way to multiply to a -48. And what we would have is a +8 and a -6. That's how you'd multiply to -48 and add to +2. Okay, so we set them equal to 0. So we take the x minus 6, set it equal to 0, take the x plus 8 and set it equal to 0. And then here we would just add the 6 to both sides and we get 6. And then here we would subtract the 8 from both sides and we get -8. Okay, so that's the first part. That's solving. State the number and type of roots. So we had two roots, and they were just these nice real numbers. Okay, so we had two real roots. That'd be the second part of your answer. All right, next. Y to the fourth minus 256. Y to the fourth minus 256 is technically the difference of squares. So we can write this as y squared and y squared. So y squared times y squared gives us y to the fourth, and then to get the -256, it actually is a perfect square. The square root is 16. So we do a -16 and a +16. Okay, when you're solving by factoring, you keep factoring until you can't factor any further. So this one is also a difference of squares, so we can factor this first one as y minus 4, y plus 4. And this is the sum of squares. We do not have a rule for the sum of squares, so we just leave that. Okay, now just like up above, we take each one and set it equal to 0. So take the y minus 4, set it equal to 0. Same thing with the y plus 4. And then finally, take this quadratic and set it equal to 0. So when I set this, I can add the 4 to both sides and I get y equals 4. I can subtract the 4 from both sides and I get negative 4. And then here I subtract 16 and then I get y squared equals negative 16, so I can square root both sides. And then I end up with y equals, remember when you square root you always have a plus or minus. And the square root of 16 is 4, so the square root of negative 16 would be 4i. You guys remember those complex numbers from earlier. So we have 4 answers, 1, 2, 3, 4. So we have 2 real, these 2, and 2 imaginary. Okay, so 2 real and 2 imaginary roots. Now, one thing you may have noticed, 2 real roots, degree of 2. 1, 2, 3, 4 roots, degree of 4. That is not a coincidence. That is something we are going to write down as a corollary to the fundamental theorem. And the corollary is kind of like an addition, like it's an expansion of that theorem. So the corollary says a polynomial of degree n has exactly n roots. Has exactly n roots, including repeats. So it is possible to have repeat roots, because if you had like an x minus 1 squared, you'd have x equals 1 and x equals 1. That would be a repeat root. All right, so the next thing we're going to learn about in this video is the Descartes rule of signs. That's a French name. It is pronounced Descartes. So say we've got this polynomial function here. That's just our generic form. It's got real coefficients, meaning no imaginary coefficients. So we've got 2 different things that we can figure out. You can find out how many positive real roots there are and how many negative real roots there are. So like on the previous page, in this example, we had 1 positive root and 1 negative real root. Here we had 1 positive real root, 1 negative real root. So that's what the Descartes rule of signs will tell us. Okay, so the number of positive real zeros is equal to this. It is the same as the number of sign changes of p of x. Or less than that by an even number. Okay, so that's going to seem absolutely insane and might not make any sense at all, but I'm going to do example 2 right now and show you what the positive real zeros. Okay, so the same as the number of sign changes of p of x. So let's do example 2 while we're trying to figure out what on earth that means. So p of x. I'm going to write our equation. I know I've got it written right there, but I'm going to write it again. So when we are looking at p of x, what we want to do is we want to count the number of sign changes. Sign changes means how many times the polynomial changes from a positive value to a negative value. So this one's negative. We change to positive. That is 1 sign change right there. This is positive, this is negative. So that is a second sign change right here. This is negative, this is negative, this is negative, this is negative. So no more sign changes. So for the number of positive real zeros, there are 2 sign changes. So it could be 2, or, and then it says less than that by an even number. So it could be 2 or 0, because 0 is an even number less than 2. So what you do is you just start with this number, and you just subtract 2 until you run out of numbers to subtract. So there's either 2 positive real zeros or 0 positive real zeros. So now let's do the negative one. So the number of negative real zeros is the same as the number of sign changes. of p of negative x. So what we do is we take the polynomial and we plug in negative x, and I'll show you how that works. Again, or less than that by an even number. Okay, so again, going to seem a little strange, but I will walk you through what that means. So we are going to take negative x, and every single time I see an x up here, I'm going to replace it with a negative x. Okay, so if I take negative x and raise it to the sixth, any even power is not going to change my sign. If I multiply something negative by itself 6 times, it will still come out positive. So this is still just a negative x to the sixth. Here, if I multiply something negative by itself 3 times, it will come out negative. So this is going to be a negative 4x cubed. Here again, negative x times negative x still comes out positive. So there's no sign change on that one. Minus negative x would be plus, and then minus 1. Okay, so let's count our sign changes here. No, no, yes. There's a sign change from negative to positive, and then yes again. Another sign change from positive to negative. Okay, so the number of negative real zeros, I have 2 sign changes, and then you just go down by an even number. Okay, so now what we're going to do is set up a little table. Okay, so I'm going to sneak it in over here. So the number of positive real zeros, number of negative real zeros, and then that leaves imaginary. So we can set up a little table. So there could be 2 positives and 2 negatives. That's one option. And since my total degree is 6, that means I would have to have 2 imaginaries because they all have to add up to 6. I could also have 2 positives and 0 negatives. That's a different possibility. And then since I have to add up to 6, that would leave me with 4 imaginaries. I could have 0 positives and 2 negatives, and that would leave me with 4 imaginary because I have to add to 6. Or I could have 0 positives, 0 negatives, and that would mean I'd have to have 6 imaginaries. So those are all of the different scenarios that you could have. All right, so in the next video, we're going to do even more with this Descartes rule.